So far in this series, we followed a request from your browser side, DNS finding the address, TLS securing the connection. But that request has to land somewhere. Today, we're flipping the perspective entirely and looking at what's actually happening on the other end, how a server, or thousands of them, handle the flood of requests hitting them every second. Byte Level Episode 4, Server Side. When you think of the server behind a website, it's easy to picture a single machine sitting somewhere quietly handling requests one at a time. For small personal sites, that's not far off. But for anything with real traffic, a popular app, a major retailer, a social platform, a single server would get overwhelmed almost instantly. Instead, large websites run many servers at once, often spread across multiple data centers around the world. Your request doesn't necessarily go to one fixed machine, it gets directed to whichever server or group of servers is best positioned to handle it. So how does your request know which server to actually go to? That's the job of a load balancer. A load balancer sits in front of a group of servers and distributes incoming requests across them, so no single server gets overloaded while others sit idle. It might do this in a simple rotating order, or more intelligently, sending requests to whichever server currently has the most capacity available or is physically closest to you, reducing delay. Load balancers also quietly handle a critical safety function. If one server in the group crashes or stops responding, the load balancer notices and simply stops sending it traffic, rerouting everything to the healthy servers instead. From your perspective as a user, you'd likely never even notice one server went down. Once a request reaches an actual server, what happens next depends on what's being asked for. Some requests are simple. The server just needs to hand back a file that's already sitting there, like an image or a static page, that's fast and lightweight. Other requests require real work. If you're logging into an account, searching for something, or loading a personalized feed, the server often needs to run application code, which might involve checking who you are, pulling relevant data from a database, combining it into a response, and sending that back. This is a lot more computationally expensive than just handing back a static file, which is part of why some pages load faster than others. A lot of what makes a website feel smart, remembering your account, showing personalized content, storing what you've purchased, lives in a database. Servers query these databases constantly to retrieve or update information. But databases can become a bottleneck if every single request has to query them directly, especially at scale. That's where caching comes back into play, similar to what we discussed with DNS. Frequently requested data often gets stored temporarily in fast access memory, so the server can return an answer without hitting the database every single time. This is why the same page often loads instantly the second time, even if it was slower the first time you visited. All of this, multiple servers, load balancers, caching, exists because traffic isn't predictable. A site might get 10 times its normal traffic during a big sale or a viral moment. To handle that, many services use what's called auto-scaling, automatically adding more servers when demand spikes and removing them again when things quiet down. So you're not paying for capacity you don't need most of the time. This is a big part of why modern cloud infrastructure looks so different from the server in a closet model of the early internet. It's less about one powerful machine and more about a flexible, distributed system that expands and contracts based on real-time demand. So that's the full picture from both directions: your browser finding the address, securing the connection, speaking the right language, and now what's actually happening on the other end to handle it all. There's one thread we haven't fully closed yet. Back in episode 1, we mentioned HTTP itself deserved a deeper look. Next time, we're finishing that, methods, status codes, and how the actual language of the web has evolved. Subscribe so you don't miss the finale.